Hello and welcome back to the Oxford MAT Livestream. My name's James and this is an episode about trigonometry. How are you doing in chat? Welcome to Oscar, Matthew, Moses, Anonymous, Sophie and Aya who have joined us in chat. On screen there, if you join Slido chat, you can also say hi if you like, which is exactly what Hannah and Len and the Integration Bible have done in some order if they appear on screen. There's a tiny bit of lag there. There they are. Good. Right. Okay. And other people joining as well, and you watching as well, whether you're in Slido chat or not, whether you're in here live or watching on the YouTube replay. One comment about my audio from Oscar. I've got quite a lot of rumbling background noise. A truck has just started reversing at exactly 5 o'clock outside my window. I hope that's going to go away. If there's some other problem with my audio, please can people let me know. Hi to Magnus and Alex and Year 10 kid coming into chat as well. Let's do the poll for how your day was. And someone here has asked me how large 14 squared is, which is a pretty squarey question. Okay, so we do this vote for how's your day going. People have voting sort of 4 or 5 stars, but I'm always watching out for these people who've joined Matt Livestream to learn about some triangles and are not having a great day. Some people vote 1 and 2 stars, and even 3 is not a brilliant day. And to those people, I suppose I say, I can offer you triangles. It's possible that triangles will improve your day. If so, then you're in the right place, because it's trigonometry this week. We've got sine and cosine and tan and periodicity of those things. Triangles all over the place. Right, okay, vote. That was very exciting watching the voting. There we go. What I would like to do, as I've done for the last few weeks, is a bit of time on revision and then some short math questions and then bits of long math questions. We've got some interesting short questions this week involving selecting graphs, thinking about how the maximum value of sine squared, what that might be. We've got something about solving equations in there as well. If you want to see the questions, even before I'm talking about them, or even without watching the live stream, then you can get the questions on the Matt Livestream page, which is www.maths.ox.ac.uk/r/matlive, MattLive, which is over there, and there's a link in the YouTube description. And that's how you can get ahead. And also how you can get the solutions. We're going to talk about some of the problems live, but not all of the problems. If you want to see solutions for other problems in some detail, you can get those on that page as well. Yes, good. Okay, we have all these options for people to join in whether or not they want to watch the live streams. But if you're here live, you can play along. Integration Bible says it's their first time actually tuning in live instead of on the YouTube replays. It's good to have you with us. Right, okay. Who have I missed? I don't think I said hi to Keller and some more anonymous people, Magnus and the Year 10 kids. Right, good, okay. That's enough shout outs. I'm going to switch chat so that I can still see chat, but maybe you can't see chat, so that I've got more space for triangle facts. I think it's time for some revision. There's a quick shout out in chat. I said I wouldn't. There's a quick shout out in chat for flashcards. If you want other Matt resources, live streams is not what you wanted. If you want other stuff, please do check that website where you can download some flashcards. I have a copy of the flashcards that I've printed out and stuck on actual cards so I can test myself on, for example, what is a prime number. It's something where it's only factors of p and 1. Oh, hooray, brilliant, okay. Or integration and all sorts of stuff. The idea is that you can sort of quickly test yourself on things that you should probably know before doing the maths. Okay, good, right. Plug for the flashcards, triangle facts. Here's the maths syllabus, or at least here's the bit of the maths syllabus that's about trigonometry. And there's a solution of simple trigonometric equations. We're going to try some of those in a minute. And we've got some identities, which hopefully you've seen before. That first one is the definition of tan, sine over cos. And then there's the brilliant fact that sine squared plus cos squared is 1, which I hope you've seen before. And then there's a fact about some relationship between sine and cosine that cos x is the same thing as sine of 90 minus x. I've written that using degrees on purpose. Math questions are written using degrees. You're allowed to know about radians, you're allowed to use radians if you like, but all the questions are written using degrees. So question in chat about the online format of the test. It's online. There'll be some sort of whiteboard material for you to write your rough work on, but that won't be collected, it won't be handed in. So rough work on a bit of whiteboard material. For the longer questions that are not multiple choice, you're going to type your explanations into text boxes on the questions. And again, you can write stuff on the whiteboard, but that's not handed in. So you have a kind of scratch pad whiteboard thing for writing rough work on, but it's not collected. The long questions are written with that in mind. They're asking candidates should expect to be justifying their answers, is I think the exact wording we've put on the website. Okay, good. Right, let's do some revision then. Here are, I think, the definitions of sine and cos and tan, where this is definition using a triangle, so I guess you have to believe in triangles before these definitions make any sense. I've got a triangle ABC that's right angled at A, and I've tried to describe what sine and cos and tan are supposed to be for that triangle using the side lengths. Maybe you've learned an acronym for this or some sort of mnemonic thing that you say. There are probably some in chat. Maybe you know SOHCAHTOA, maybe you know one of the other ones. Good. I've written it out there in the revision notes just to be super clear as ratios of side lengths, describing the side lengths by AB and BC, things like that. Okay. Brilliant, shout out. So there is a sample paper. What are we calling it? A practice paper. It's on the MAT page. So MAT Livestream stuff. It's got preparation materials. That also links to the overall maths admissions test page on the maths website, which you can actually get to by typing all of that without LIVE. The MAT page has got a link to test paper. Anna's thinking about the unit circle instead. That is a good idea. I can't remember what order I learned these things in, but if you draw the unit circle, then some people think about it like this, right? Where you have some angle above the x-axis, so angle theta, to get to this particular point on the unit circle, and as you change theta from 0 to 2 pi, 0 to 360 degrees, you get all the way around, and that moves this point around the circle, and the coordinates of that point are just cos theta and sine theta. So as you move around the unit circle, anti-clockwise, counterclockwise, the x coordinate starts off at its largest value and decreases, that's cosine, and then eventually comes back up again, whereas the y coordinate starts at 0 and goes up and then back down again, and then goes negative and then comes back up again. That's sine. Good. People are posting excellent acronyms and mnemonics for sine, cos, and tan. Which one's which? So yeah, hopefully the shorter the better. If your anecdote or if your mnemonic is too long, then it's gonna be hard to get through the triangles, I guess. I suppose Anna's comment about the unit circle, the idea is that this radius here is 1, radius of the circle, has the length 1, so the hypotenuse is 1, which in the language up there is something like, if the length BC is 1, then these things have got quite simple definitions. I guess the idea is that you scale the triangle, maybe if you scale the triangle, the angles stay the same, but the lengths all change. They all change by kind of same factor when you scale up a triangle. So there's some sort of intrinsic link between the angle and not a particular side length, but the ratio between the side lengths. I guess that's where these come from. Anyway, good. Okay. And earlier I said this was definition. Now I'm saying it's a result that follows from that triangle, but however you want to think about it, tan is sine over cos, not the other way around. So it's, I guess, quite easy to mix up sine and cos, but that can have terrible consequences when you divide. Importantly, tan theta is quite different from the others. Tan theta can be extremely large. Sine and cos are bounded, but tan is unbounded because it's dividing by cosine, and that value of that cosine could be quite small. Technically, tan with that expression and with those triangles, tan of 90 degrees is not defined in either of those worlds. Some people might say it's infinitely large, but that's very helpful. Anyway, Pythagoras' theorem for a right angle triangle, which we proved many times in many different ways. It's maybe the theorem I've seen the most proofs of, although only one or two spring to mind immediately. The square on the hypotenuse is equal in size to the sum of the squares on the other two sides, which leads you, if you think about this particular triangle on the right, to the result that sine squared plus cos squared must be 1, which is quite nice. So those things are bounded. Cool. Laying this out in such a nice order. I'm really pleased with how these revision notes have come together. I bet this is not the order you do these things in the classroom, but whatever. We're revising things quite quickly. Do tell me in chat to slow down if you want me to spend more time reminding you about things you already know. I'm hoping that this is a relaxing look back at things you already know. Yeah, looking at the triangle the other way around. So here we've got the same triangle, but looking at it from the other angle. So if you look at it from over here, then you have a hypotenuse, an opposite side, and an adjacent side. But if you look at it from the other side, if you look at it from over here, then nothing changes about the triangle. You're just looking at it from a different point of view. You're looking at this angle over here, and this is now the opposite side, and this is now the adjacent side. There's got two ways to look at the same triangle. They give you these facts to say, well, the angles are obviously related in this triangle, because angles in a triangle have up to 180 degrees, and somehow what was cosine of this angle is sine of that angle. What was adjacent is now opposite. If you just move your gaze to look at the other angle. Okay, functions are all periodic. Sine and cosine, you can add 360 degrees and get back to where you started. I guess that's pretty clear over here in the unit circle picture that Anna gave us. If you increase theta by 360 degrees, you get all the way back around again. Same coordinates, same values. So that's pretty good. Tan is a little bit different because tan's the ratio of these things. If both of them go negative, then they might have the same ratio earlier, even though cos and sine have not yet come back to their original values. You could end up with the same value. I suppose you could draw in these lines, right, to say cos theta is constant on that line, takes the same value. Any point on there, cos theta takes the same value. Sine theta is constant along this line. And tan theta is constant along quite a different line, which is this one. Tan theta constant. So including going out the other way. Theta increases by 180 degrees, but same value of tan, same ratio of sine and cos. Magnus has looked ahead to the questions, has a question about the questions. I'm going to catch up with you in a second. Tan 45x is an interesting expression. I designed that question in particular, Magnus, in order to catch people out. When we get to it, it's question 4 if you're playing along. When we get to it, I'm hoping that I've caught somebody out. Okay, so that I can make a point, so that we can learn a thing, not because I'm mean. Right, okay. There are some more expressions that sine and cosine do here. Thinking about what happens on the unit circle. as you move a little bit above the x-axis, a little bit below the x-axis, you can generally work out that cos theta is. You can generally work out that cos theta is symmetric, about 0, and sin theta is kind of anti-symmetric. It's an odd function. Cougar's asked, are things written on diagrams on the question paper marked? And Cougar, I think I need to encourage you to check the MAT page for updates for the MAT this year. The MAT is going to be on a computer screen, and you're going to answer by selecting options for the multiple choice questions and typing answers for the longer questions. So you cannot write on the diagrams because they are on a screen, and the question paper is no longer made of paper. Right, okay. Yeah, sorry. Oh, sorry, they did know that, but they also forgot. Sorry. I guess that's the theme of the revision section, is me telling people things they already knew, but in a sort of reminding kind of way. Right, okay. More interesting triangle. Oh, here we are. The convention with these triangles, picture at the top. Convention with these triangles is that the side called A is the one that's opposite angle A, alpha, corner A, but that's just a convention. You can call your triangle sides whatever you like. And then there's facts about the area of a general triangle that's not necessarily right angled. So I've got 3 formulas for the area. Might like to think about that a little bit. You've probably learnt one of these in the classroom, or one of these in school, or one of these by studying A-level maths or equivalent outside of school. I've written down all 3 of them, just in case. Can you see what I've done there for those 3 expressions for the area of the triangle? Magnus asks about, can we use scrap paper? You get given it's a kind of whiteboard sort of thing. In the test center, you get given some stuff to write on. You can't take in your own paper, and it is a kind of clean whiteboard so that it's reusable for the test center rather than having lots of paper. I think it's also a security thing that you can't take in your own notes. You can't remove any notes, so not scrap paper. Keller wants to ask about other trigonometric functions. Keller's heard of 3 more, which maybe you've heard of as well. Sec, cot, and I guess we should go cosec as well. These are just defined to be 1 over tan x, 1 over cos x, and 1 over sine x. You're not expected to know those definitions for the math submissions test. Oh, they're slightly underneath my camera. There we go. You're not expected to know those. They're not secret knowledge, but we don't expect everyone to know what they are, which means that we won't use these in a question without telling you what we mean. The reason they exist is because triangles have got 3 sides, and when you're building a fraction, you have 3 choices about what to put up here, and you have 3 choices about what to put down here for 3 of the sides of a triangle in your fraction. 3 choices, so that gives you 9 functions that you could define based on your triangle, but 3 of them are the identity function, not just 1. If you pick the same side for the top and bottom, so maybe you're supposed to choose different side lengths for the 2 bits of your fraction, and that gives you 6 functions. Now it's still kind of true that half of them are just reciprocals of the other, and tan is just derived from the other 2. There's only really 2 fractions that you can make, but it's sort of, in terms of counting, it's kind of 6 of these that kind of could exist. People are saying mock paper, practice paper, sample paper, whatever you're calling it, there's a link on the MAT page. Near the top, describing the test format, there's a link to, I think I'm calling it a practice paper, but it's up there. Don't get too excited, it's made of past paper questions. So it's made of mostly questions from 2020, actually. mostly questions from 2020, but just in the format so you can see what multiple choice looks like on a computer screen. Really don't get too excited. And Dylan asks about double angle and addition rules. You are not expected to know those for the maths submissions test, because it's one of the things that some people learn later, some people learn earlier. Good example of something that I would have to put on my syllabus, I think, at the top of the first page. I would think I would have to say double angle formulae. And addition formula are even more complicated. Is there a tan rule for triangles? If there is, I don't think I know it. I don't think I know a tan rule for triangles like the sine rule and cosine rule. I guess you could build one if you wanted one. I know an expression for cos in terms of the side lengths. I know an expression for sine in terms of the side length and the in circle. Yeah, it will be a bit derivative, I think. The thing I'm thinking of anyway. Right, 2 rules about triangles, and then we're done with revision. The cosine rule, you can think of that as being a slightly better version of Pythagoras, Pythagoras' theorem. It's got a special case, you see. A squared is equal to b squared plus c squared if cos alpha is 0. So if you have a triangle where cos alpha is 0, then hey, you can write down a squared equals b squared plus c squared. That's pretty nice, and that's a fact you know, that's Pythagoras. The cosine rule, slightly better, I say, because you could set cosine alpha to be something else if you have a different triangle in mind. So that'd be nice. Good. Okay. I don't think I've mentioned in here, if I said this, you should probably know the values of some of these things in terms of sort of special triangles. Only a couple of them, right? But there are some special triangles where we can work out the values of these things. That is not a good picture of a triangle. I'm going to stick with it. So like in this triangle, for example, and there are some angles here which are both 45 degrees, and that helps us work out what cos of 45 degrees is, what sine of 45 degrees is, and also what tan of 45 degrees is. For example, tan of 45 degrees is just 1, which is quite nice. Sine and cosine are equal for this isosceles triangle. There's another triangle that you might like, which is the 60, 30, 90 triangle. That one's fun because it's half an equilateral triangle. So it has, because it's half an equilateral triangle, this is something like 1/2. This is √3/2. Pythagoras, side length, mumble, squaring. I guess maybe people normally write this 1, 2, √3, whatever. It's all ratios, isn't it? It's all ratios. I'll say something like tan of 60 degrees is √3. I suppose we can do cos of 60 degrees is 1/2. Good. I usually have to draw something like this to remind myself of the values. You are much more practiced than me right now, I think, and maybe you can do these without thinking at all. Sophie wants to know about what it says about extra time. I think it probably should be when you register. There should be an option to ask about that, to make a request. Some of the details are still being worked out. We would obviously like to do whatever you normally get. Year 10 kid knows some sort of hand trick for working out special values. Oh, have I seen this? Is it something like counting on your knuckles to work out √3? No. Okay, never mind. Look, whatever you've got for knowing the values is probably good. I can never remember the tan values. Yeah, it's tricky, isn't it? Because some of the tan values are larger than 1. The sine and cosine ones, it's all right, but the tan values are occasionally 1 over the number that you were thinking of, which is quite a big difference. Anyway, shall we do some questions? I think it's probably good. We've got things like the cosine rule on the screen. I didn't say anything about the sine rule. There it is. We've got sine alpha over A is sine beta over B is sine gamma over C. Nobody really engaged with my suggestion that you think about the 3 formulas for the area of a triangle at the top. That comes from, maybe it's too obvious, it comes from thinking about the triangle 3 ways round in terms of which angle are you looking at to use maybe you learnt the sine rule for a particular angle C, or gamma or something, angle gamma at corner C. Maybe you learnt the sine rule for a particular angle. There I've just interpreted that for each of the 3 angles of the triangle. There's something powerful there, right, about you learn a formula where the letters mean very particular things, but then you see it in a context where you need to work out how those letters line up with the things in your formula. For example, maybe you know totally separate, but maybe you know the quadratic formula as being this expression in terms of A, B, and C for this quadratic. And then maybe you come across this quadratic in the wild, and you would like to work out how to solve that one using your formula. Then you have the kind of challenge that B is not B, A is not A, and C is C. Okay, great. But you have to do some switching, perhaps. That's kind of what I've been trying to do at the top to work about them. Yeah. So there is some sort of hand trick that I've forgotten for doing values of sine and cosine. The chat is sort of explaining to me, giving me more tricks. Yeah, so as long as, for the sine rule there, we're saying that each of those fractions is equal, you can, if that number is not 0, then you can flip those things the other way up. So some people learn it as A over sine alpha, B over sine beta, C over sine gamma. That one makes me more nervous because if these things, if sine alpha is not 0, which it's probably not for a sensible triangle. I just need my little terms and conditions, right? But provided these things are non-zero, I suppose it's good enough to show you that if one of them is 0, then I suppose all of them have to be 0. All of the angles would be 0, or 180 degrees, which makes me think of the degenerate triangle. Have people seen the degenerate triangle? I guess it's a whole family of, a whole collection of degenerate triangles. The degenerate triangle is one with no area, where all the angles are either 0 degrees or 180 degrees. That's sometimes called a degenerate triangle, which sounds a bit dismissive, and I think that's on purpose. These triangles are not really triangles, they only sort of have 3 sides. So maybe my sine rule shouldn't include them anyway, right? Yeah, if one of the angles is 0, is that even a triangle? Is that even a triangle? Aya in chat, I think, pretty clearly does not think it is. Yeah, it's a Magnus is calling it a digon for a 2-sided shape. It's got this extra corner that's kind of sort of a corner. It's a corner in name only on one of the sides to give it 3 corners. I don't like it. Don't like it at all. Right, okay. We are moving, I think, inevitably towards revision questions. We've got several of them on the screen. I think, was it Magnus wanted to talk about question 4, where we go from question 3 to question 4, solving one equation and then solving this kind of variant equation where I've replaced x with 45x. And I've already told the live stream that I'm trying to catch people out, so we will see. Question used to have a hint on it, but the hint was designed to make sure no one got caught out. Where's the fun in that? So let's see if I've caught anybody out. Line with extra steps, fancy line. Yeah, cool. Right, let's get the degenerate triangle out of here. Let's get that out of here. I'm hoping that people can find the area of an equilateral triangle without my help. I was going to say. Sounded a bit weird. I would advise splitting it into 2 right-angle triangles down the middle. Yeah, so Magnus would like the number of solutions. I actually think the number of solutions is harder than explaining what the solutions are. Like counting them is a bit harder than saying what they are. I guess listing them is tricky because there might be lots. Right, okay, so maybe this is the thing I'm going to discover in question 4. Okay, let's vote for, I think I is voting for question 7 and question 12. Oh yeah, 7 uses a sequence or series. Let's just quickly show people the questions. If you're watching the video and you haven't seen the website, then let's have a quick look at what we've got. So we've got 6 is a bit strange. 7 has an infinite sum in it. Write it as a single expression, not an infinite sum. And then there's change of variables from cos to sine, which is hopefully okay. Some simplification, including something that is secretly the angle addition formula. And then some very particular triangles for you to tell me facts about. Question 13 is a very particular triangle, the 8, 13, 15 triangle. Question 11 is just some random triangle. I hope I don't have to work out its area. I think it's a nasty number. Or is it the opposite side that's a nasty number? Anyway, so we've got solutions to equations. Oh, there's an anonymous person voted for 6. Quick look at 6. Yes, okay, we'll get there, we'll get there. Yeah, good. Okay. So I think that means that I've got permission to skip question 2, but I am going to talk about question 2 anyway, because I want to make a point about what's going on. So we saw a graph of sine x actually way back in graphs and transformations when we did graphs of lots of stuff. And sine looks something like this, where that's 360 degrees, that's 180, that's 0. I think it's negative over here, but we're just looking between 0 and 360 degrees. So just this bit of the oscillation. And we're asked about values where sine x is 1/2, which is a bit like solving. I know this is daft, but it's a bit like solving y equals sine x and y equals 1/2, looking for simultaneous solutions of this. So I've introduced the letter y there for almost no reason, except it gives me 2 things to draw. I draw y equals sine x and y equals 1/2. You know, if you're going to try and solve these, then probably the first thing you do is to plug in 1/2 for the value of y, and then oh yeah, we're back to the question. So you might like to think about that. So I think I just need to find these 2 values for question 2. And if I really think about it, then I've seen this triangle before, where sine opposite over hypotenuse is 1/2. I've seen this triangle before. This is the 60-30 triangle, which I suppose gives me one of the solutions. The thing that I'm encouraging people to be really careful with is that we have another solution over here, and you can get multiple solutions because this thing has lots of symmetry. It goes up, but it comes back down again. This solution over here, sine is symmetric about 90 degrees, or said differently, going up from 0, you see the same values as you do coming down from 180 degrees, going this way out of the origin. To the right, you see the same stuff as if you came in from 180 degrees. Sine of 180 minus x is the same thing as sine of x. Anyway, right, this is 150. Okay. Yes, good. Okay, so there's 2 solutions for question 2, which nobody asked me to do, but I just want to set the tone a little bit before we look at other functions as well. So tan x being equal to 1, we already saw that 45 degrees works, but we might suspect that we should find some more solutions or check for any other solutions. And that's where you get into, what does tan look like? I think tan looks like this. Where you have a 0 here, and then it blows up at 90 degrees, and then it's very well behaved, and then it blows up again at 270 degrees, and then it's just got back to being 0 again at 360. Not to scale. Look at my terrible spacing there. 90, 180, 270, 360. That maybe it's not that bad. Okay. Where's it equal to 1? Well, if I draw this line in, this is part to the right of 360 degrees, but there's a couple of solutions, so I should try and find the other one as well. If I add 180 degrees, that's the period of tan, I get so does 225 degrees. Okay, Yeah, so then question 4, there is a graph transformation, says Noah, which is correct. You can think of that as a graph transformation. The graph transformation has squashed tan. My picture was already quite squashed, so I'm going to try and draw an even more squashed version of it. Whoop, by a factor of 45, there we go. Whoop, which is squashed down that point and that point. This is still the number 1. Squash down these numbers to be 1 degree, and over here 225 divided by 45, well, it was 1 lot of 45 plus, I guess 180 degrees, it's 4 lots of 45, so this is now 5 degrees. So squash. So if you take your previous numbers and divide them by 45, you'll get the values to put in, such that when you put them in the new function, they get multiplied by 45, and then they turn back into their previous selves, these previous numbers, where tan of those numbers is 1. And here's the kind of trap, I suppose, we're not done. And the reason we're not done is that the range of x has not changed. But going from question 3 to question 4, we've successfully replaced x with 45x in the equation, but so far we've been acting like the x in the inequality has been replaced with a 45x in the inequality. And there's a mismatch in question 4, right? That the equation has been updated to have a 45 in it, but the inequality, the range of x, has not been updated to have a 45 in it. That's the trap. That 1 degree and 5 degrees both work, but the question is still asking us, like it has in question 2 and question 3, the question is still asking us about all the solutions up to 360 degrees. So we've got, and Magnus has gone for the punchline. We've got a lot of solutions to find. There are quite a few of these, because I suppose without the restriction on the range, back in the previous question, we could have kept going, right? We could have gone for 45 plus 360, that would be the next one, over here. That one was out of range, so we ignored it. But now, after dividing by 45, it's fair again, isn't it? That would be 9 lots of 45 overall. So that would be here, what is now 9 degrees on the new chart. Yeah, good. Okay. So I think the solutions are, I think on the previous one it was periodic with period 180 degrees, and after the 45, the factor of 45 squash, it's now periodic with period 4 degrees, because 180 divided by 45 is 4. So I think it's periodic with period 4 degrees, so it's 1 plus 4n. So x could be 1 degree plus 4n degrees. Where am I going to put the degree symbol? I don't know where to put the degree symbol. I might put it here and here. That feels bad. Anyway, never mind. And then I'll have a think in a second. Do I want 90 of these? I'm worried that if I add 90, if I put n as 90, then I go, I think, to 361. I'm worried it's 1 every 4 degrees. Am I being silly? Oh no, n could be 0. N could be 0. Okay, cool. I forgot that 1 degree is 1 plus no lots of 4. That's where we started. Out by 1 error. I made it sound like it was your out by 1 error, but it was actually my out by 1 error. Okay. So that should be a whole number. "90 solutions. Wow, it's quite a lot. Yeah, so 357 is the last one. Let's mark that in here. Let's put ... and then go for this last one. 357 degrees. I think, yeah, 4 degrees less than the one I was worried about, which is 361. Okay. Hey, somebody is here from just finishing Unique. Hello, if you are on Unique. Nice to see you again. Anonymous has been caught out. So, yep, sorry for catching you out, anonymous person. Sorry, I got you. We learned a thing about, I guess what we've learned is a thing about checking the range. And I guess it maybe feels like a trick question because the range didn't change. Do I mean less than or equal to 89? Yes, I do, thank you. I'm still out by 1. Look at that. Despite saying out by 1, I was out by 2. Sophie says it repeats over and over. The only actual solution 1. No, I don't think there's anything wrong with 5. The tan of 45 times 5 really is 1. So that really is a solution. Oh, off the bottom of the screen. That really is. It really is a solution. I mean, just as good as any other thing that works in the equation and is in the range. Are all angles assumed to be measured in degrees on the mat? I don't like the word assumed. If an angle is given, it will be given in degrees, not radians. Not because there's anything wrong with radians, just we think that some people doing the test haven't seen radians yet. So if we could tell you an angle, we'll tell you the angle in degrees. Well, yeah, I don't think there's anything assumed about it. We have to be quite clear. Yeah, so radians are A2 maths in England. If you're doing maths and further maths in parallel, then you might not see radians until halfway through your last year of school. So you might only see radians, a few months before you're done with school or sixth form. They're worth waiting for. Okay, right. Yeah, all in degrees. You're allowed to know about radians, of course. You're allowed to know about so much stuff. That's like, my goodness. You probably know loads of things that are not on the MAT syllabus. Right? Probably good for you to know at least some things that are not on the MAT syllabus, just in life, right? But the MAT syllabus is limited partly because you and the person sitting next to you might have learned quite different maths so far. It's a test that you take maybe midway through your sixth form experience. Okay, there's now going to be some sort of contest in chat about radians and degrees. Yeah, okay. Write down 3 expressions for the area. Why have I even set that question? It's a right-angled triangle. It's a right-angled triangle. I guess you could write down expressions in terms of sine 60 degrees, sine 30 degrees, and check that you know the values of those things. Should be able to work out the area of that right-angled triangle. I genuinely can't remember what that question's for, sorry. I think I wrote it without really thinking about how hard it was. Okay, 6. The only thing I was expecting for 6. I've tried to do a kind of trigonometry algebra mashup sort of thing here to get you thinking about these as to think about x as a kind of variable that you're changing. Anyway, I hope you tried squaring this expression so that you would get something like oh, hello. What have I done there? I've done a typo and then I've confused my whiteboard. There we go. Okay, expanding it out gives you something like this, second time lucky, which maybe you would think of doing because then you get something like cosine. The gimmick of this thing is I just want to rename that and call it u, so then I've got cos squared plus sine squared, but wait, that's 1. So 1 plus 2u or something like that. Good, okay. Wait, so why is everyone telling me that? Why is everyone telling me the value of that? Yeah, I was expecting 2u plus 1. Nobody's saying that this is equal to 0. If it's equal to 0, then I'll let you rearrange it. But yeah, it's an expression. It's an expression. Its value will be something in terms of u. If it's equal to 0, then sure, u is minus 1/2. If it's and also sine x cos x would be minus 1/2, but it's just an expression like this, then the best we could say is that this expression is just 1 plus 2u. Okay, and that brings us neatly to 7. If it's 0 though, hang on, if it's 0 then this square is 0. Sorry, people in chat have, for people watching the replay, some people in chat have told me that u is minus 1/2, which means I think that they're imagining this term to be 0, which gives us this interesting statement, I think. Not intended really by, not intended, but interesting, that this is true if and only if cos x plus sine x is equal to 0. That's not nothing. Let's rename that as well. That's not nothing. It's kind of cool, right? Cos x times sine x is minus 1/2. If and only if cos x plus sine x is 0. Yeah, looks good. The person in chat who asked me about the double angle formula and the angle addition formula, that person in chat is probably thinking, that's not that clever, because that's just pi over 4, and then it's just... I bet you are thinking that. You've seen cos x plus sine x before. Anyway, right, okay. You've probably seen cos x times sine x as well. Maybe you've got strong feelings about this, including the number 2. Interesting, something going on there? Is there something? Yeah, okay. I'm sort of trying to give extra homework to people who happen to have done that bit of maths already. To like, if you've seen 2 times cos x times sine x before, what's going on here? What's all this? If it's related to a thing you've heard of, work out why. Well, you can say that about all the questions, can't you? If this is related to a thing you've heard of, work out why. Right, I'm going a bit silly, and I'm on question 7. Okay, so next week we've got content about sequences and series. So this is a little bit out of sequence. We will learn how to do infinite sums of a very particular format. Lots of infinite sums are really hard because you have infinitely much adding to do. And this is of the very particular format that we're going to learn. So sort of next week, sort of trailer or spoiler, we're going to learn how to do this sum forever, with provided that the size of r, it's between, if r is between -1 and 1, then we're going to learn how to do this sum. We're going to learn that it's equal to a over 1 minus r, which is pretty powerful. It's quite a nice result. It's much better to do this rather than the infinite amount of stuff here. So yeah. So that's, I think, what we can try to do, because it's that with, yep, Integration Bible in chat tells me it's precisely one of these with a equal to the number 1 and r equal to, this is a bit weird, minus sine squared x. Good shout in chat. So it's an example of a geometric series. Something you can do with the flashcards is turn them all upside down, and then look at the back of a card and try to remember what it was. So if I look at the back of this card, it says the only factors of p are 1 and p. And then it's kind of the reverse game to remember that that's a prime number. So learning both ways is quite a bit harder than just learning the forwards direction. Anyway, yeah, other suggestions are coming through in chat, which I quite like. The intention was that you would just go, oh ho, this is just this, and then try and write this in terms of cos x because it says to. But this is, there we go, in terms of cos squared x, in terms of cos x. And there are other suggestions. Difference of 2 squares is really good because there are lots of squares in there. If you group terms together, then you get, this is tempting, isn't it? 1 minus sine squared is just cos squared. I see that's really That's really tempting to go for that one. And then sine to the 4 minus sine to the 6 is just cos squared times sine squared. So maybe we're onto something here. So group this. So here's a grouping of the terms. Oh, my Slido window has decided that it's not happy with me. So if you don't really like the minus signs, then this is a way to avoid having geometric series with minus signs in it. But more seriously, perhaps, this is a way to get something that looks like cos squared straight away, because this term at the front is just cos squared. And then this term is sine squared x cos squared. And this term here is, I mean sine to the 4. And then this term here is 1 minus sine squared with sine to the 4. And this one is 1 minus sine squared but with a sine to the 8. Yeah, I think that works. Suggestion from chat, pair the terms together, do something like this. And then this is a geometric series with first term cos squared x and common ratio sine to the 4x. So if you sum this one, the sum is just, I say just, it's just this. Wow, it's a bit complicated, isn't it? Before you convert that sine to the 4 to cos squared squared or something, it's probably good to realise difference of two squares down here. One minus sine squared is the same thing as cos squared, and now I'm back to this expression, 1 over 1 plus sine squared. I'm going to get back. Yeah, okay. Keller's got an expression with n in it, which looks good actually, except so you've taken the sum of the first n terms. For me, the dot 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 means keep going to infinity. So if you take n to be really large, using the geometric series formula in the case that you're doing the infinite sum, and so taking n to infinity, lots and lots of terms, then I think the thing in chat there turns into this, which I haven't quite simplified, have I? There we go, a bit better. Okay. Provided you have infinitely many terms. There's a thing I've mentioned there, of course, which is that I want the thing to the power of n, I want that to go away. So if I want that thing with n to go away, I need the ratio here, the number r, to be between -1 and 1, not equal to either of those things, which is why I've excluded 90 degrees. Because if you put in 90 degrees, then all of those sine squareds are 1, and then we have a pretty bad sum, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, and that one doesn't converge to anything. The limit doesn't exist. The wording "not an infinite sum." Yeah, that is a good point, that the phrase "not an infinite sum" immediately after something that is an infinite sum. So I mean not as an infinite sum. Instead of as an infinite sum. Yeah, instead of. You're right. Putting "not an infinite sum" was maybe not very helpful straight after writing an infinite sum. Geometric series are on limits rather than off limit. They are one of the only topics that's from the second half of A-level maths. Some people might be learning them right at the start of year 13. I think some people might be learning them next week when we do the revision session for sequences and series on the MAT Livestream. So some people might see that. Yeah, sorry, I meant I didn't want you to write it as an infinite sum, not that. But I guess what I didn't want, it's poor wording on my part, but what I didn't want was this. You know, just switch each sine squared for a cos squared, and then move on without really thinking about what was going on. I didn't want this, and I didn't know how to ban this. I mean, this sum's really weird, especially if you start expanding it, then things go really, really wrong. Anna is learning about this next week, so yeah, okay. I like the sequences in series episode because I get to actually teach people some maths that they don't already know. Someone taught themselves sequences in series just to do that question. I'm really sorry that this was the first question you saw on this topic. It's a weird question. Right, good, okay. We're learning maths. That's nice, isn't it? Cool. Let's check. Year 10 kids? Year 10 kids definitely not seen infinite series before. Maybe they're also learning sequences in series. Okay. Right, so if you do A2 in 1 year, then if you do the full A2 maths in 1 year, then you've already seen it. It's still one thing. I might have read it somewhere else. Okay, right, what are we doing? I've forgotten which questions we're looking at. Let me scroll out. There was a request for 12, which is skipping a little bit, but that's okay. I'm happy to skip to 12. There's 5 to 6. For add math. Oh, that's good. Good topic to do in additional maths. 5 to 6. I think I'm going to talk about the triangle inequality just a little bit. So, from the fact that cos alpha is between -1 and 1, and the cosine rule, you can deduce this kind of limit on the lengths of the sides of a triangle, which is a bit obvious. It says that the longest side of a triangle is shorter than the sum of the other two sides. A straight line is the shortest distance between 2 points, not weirdly going along the other two sides of a rectangle. You should just go straight. That's a shorter distance if you go direct. All of those things. The triangle inequality. You can prove it though, and I think that's nice. And in this case, I've set the side lengths to be greater than 0. So we're not doing. Wait, no, that doesn't avoid there. That doesn't. Oh, the side lengths are not. That doesn't avoid it either. That omits the 1, 2, 3 triangle. I have not correctly banned the degenerate triangle. Interesting. Yes, there's lots of nonsense about series on the internet, and some of it's more advanced nonsense than other advanced nonsense, and it's quite hard to tell when you're starting out which things are a bit silly. Right, good, okay. Cosine rule, it says to start with, and there's a clue about cos alpha, so I'm going to take that sort of cosine rule, I think, like this, where the cosine rule is a squared is equal to b squared plus c squared minus 2bc cos alpha. And I'd like a statement about b plus c compared to a. So I suppose I'd like some bounds on how big a can be. I've got if b and c are fixed numbers and a is also a fixed number. Well, does that make any sense? Well, I guess I'll imagine keeping b and c fixed, but changing the angle to see what happens. And what I expect to happen as I change the angle between lines B and C, the sides B and C, as I change that angle, I'm expecting to see that there's kind of a maximum that side length A could get to, and some sort of minimum that side length A could get to, depending on the value of this cos alpha term over here. So we've got some bounds on cos alpha, which means that I can say something like, since cos alpha is less than or equal to 1, that means that minus 2bc cos alpha is greater than or equal to minus 2bc. So b squared plus c squared minus 2bc cos alpha is greater than or equal to b squared greater than or equal to. Sorry, I think I just tried to say greater than or equal to as if it was one single word, and that's really not very good, is it? b squared plus c squared minus 2bc. What I've done here is I've used the fact that we're given about cos alpha, but I guess it's the fact we're given and just a true fact about cos alpha that it's bounded above by 1. I wanted to see what that bound would do, because I know that I'm aiming for a bound to do with a, and I have some bounds to do with cos alpha, and there's lots of things between where I am and where I would like to be. So I'm trying to build up to it. I'm trying to be really careful with minus signs. Remember, multiplying both sides by -1 flips the direction of the inequality. Adding b squared plus c squared is fine though. Okay, this thing on the right that I've got down to is just b minus c squared. Thank you, Noah, in the chat. Playing along, there we go, which is just b minus c squared. Is that what I wanted? Not really, but it is kind of interesting. It says that a squared is greater than or equal to b minus c squared. Did I want that? Not really. I guess I know these things are positive things, so a is pretty large, it's larger than b minus c. That's not what I wanted. I wanted something with a b plus c. Oh dear. Let's read backwards and work out where we could have got a plus sign from. So if we wanted a plus sign at the end, I also wanted the inequality to be the other way around. Plus sign here would be a plus sign here, would be a plus sign here. So we need a plus sign here and here. So we'd want plus signs on both these sides. So this line would have to read something like cos alpha is larger than, well, no, because it's b multiplied by minus 2bc. So this would have to be, right, it's the other one. I need the other one. Yeah, if you say cos alpha is larger than -1, I might get exactly the thing that I'm looking for. 2bc with a minus sign that flips this direction of the inequality again. And then if I add on the b squared plus c squared, minus 2bc cos alpha, I'll get, these are a totally separate argument, but also it's kind of the same argument, but this time better. There we go, that's b plus c squared. So then I've got on the left the thing that appears in the cosine rule, it's a squared, and on the right it's less than or equal to b plus c squared. Both these things are positive, and we're looking at their squares. So a is positive, b plus c is positive, so it's positive. Got to check they're positive. So a is less than or equal to b plus c. Cool. Hooray! It's the thing in the question, but with an equal sign. I thought that I'd banned so they could be equal. If a is 3, b is 2, and c is 1, then they might be equal. But I don't think very much of that triangle. I suppose I don't really want cos alpha to be 1 or -1. Those are pretty degenerate values for cos alpha to take. So maybe I should have banned it at the start of the question. Nah, I should just have it down here, shouldn't I? So the second line incorrect, since multiplying by cos alpha makes it smaller. I don't think I'm multiplying anything by cos alpha. I think I'm taking a true statement and multiplying both sides by -2bc. So this is given, and then this is times -2bc, which is definitely negative, which is why I flipped it. I don't think I've multiplied anything by cos alpha. I think I'm okay. And then I'm adding stuff. Adding is fine. Adding doesn't scare me at all. Okay, so one side is less than or equal to the sum of the other two sides. Cool, okay, we've got to 6 o'clock, we're at the halfway point. If you've been looking at the screen for the last hour, like I have, then don't forget to look away from the screen, blink, it's probably good for you. You might like to take a break. No, don't worry, that is fine. Example of when will A be exactly B plus C? We can actually work that out from this logic, right? So if these things are equal, then the previous lines would be equal. So these things would be equal. So these things would be equal. So this would be equal. Cos alpha will be exactly if cos alpha is exactly -1, then these lines are actually equal. And that happens if alpha is 180 degrees, which is pretty stupid. 180 degrees, wow. Like this. 3, 2, 1. B is 3, B is 2, C is 1, for example. Degenerate triangle. And I mentioned these before, but here they are again. A triangle with a 180-degree angle is not very much of a triangle. Some people don't count these as triangles at all. But to answer your question, when would these things be actually equal? I think if you read through the working again, these things are actually equal if cos alpha is 1, minus 1, whoops, minus 1. So actually only really 180 degrees, plus multiples of 360, but doesn't change the geometry of the shape, if you can even call that a shape. Right, okay. What am I doing? I think we're switching to math questions, if people are happy. I quite like that I did both of these, by the way. We did both. This one got us down to a result we weren't quite looking for, but then this one got me down to a result that I was looking for. If at first you don't succeed, try again, and hopefully your second attempt might be slightly different if the answer that you're looking for is slightly different. There's an alternative way here to say, well, so far we've only assumed that B is greater than C. If you relabel the sides, if you do a quick relabeling, then you can move, what can you do? You can move C onto the left-hand side, move it onto the large side, and pretend that B was the largest side all along. Pretend that B is larger than A. So that's obviously not quite the same letters as the ones in the question, but it's morally the same thing, that the largest side of the triangle would still be less than the sum of the other two. Nowhere so far over here have we used the fact that B was positive. I considered saying all of that at that moment, but then thought, no, I've already had one moment of relabeling a triangle and moving things around. Let's just do the more sensible thing. Okay, right, math questions, I think. Yeah, thank you, Xusheng, in chat as well. Got Xusheng moderating chat and also moderating people's triangles. Xusheng has come down on the not a triangle side of the degenerate triangle discussion. Right, good, okay. Let's look at some math questions. Here's one, for example. So this is back to thinking about these things just as functions, which could have a largest value. There's no particular triangle in sight in this question. We're not being asked to do anything triangle-y with it. But that doesn't mean that no triangles will turn up along the way. It's entirely possible that we'll do some tricks to this or do some steps of working and then discover that we're suddenly faced with a triangle sort of question. So I think I'll get help from chat on this one. We're going to do all three of these short questions as a kind of a sort of warm-up still. We're 1 hour in, but we're still doing a bit of warm-up here. We'll talk about all three of these. Suggestions from chat, please, of how do you get started with a question like this? Which one's the maximum value of this? 4 sine squared x plus 4 cos x plus 1, all to the power of 2. Okay. And I'll wait for a couple of people to have something in chat, so that we've got other opinions. And so I can drink some water. Lots of people suggesting the same stuff, including Anna and Hannah and Aya and Magnus and Anonymous and Tristan and Noah and lots of people want to switch the sines into cosines, which I will happily do for you. A couple of votes in there for differentiating the thing, and I mean, it's multiple choice. Anything you do counts if you get the right answer. I think this function is quite hard to differentiate, and I want to say that being able to differentiate cos and sine is not on the math syllabus. Not everybody who does the test knows how to differentiate cos and sine, which, two ways to react to that information. You might think, haha, I do know how to differentiate cos and sine, and you can't stop me, off I go. Or you could think, wait, it must be possible to do this question without differentiating cos or sine. Because it's not in the syllabus. Some people maybe don't know how to differentiate cos and sine. Which is maybe why we're going to try and avoid doing that. But let's go. So 5 plus 4 cos x minus 4 cos squared x unless I've made some sort of horrible error. I haven't done anything with this big square out the side. There's a suggestion about completing the square. I like completing the square here. I think that's a good idea. Am I going to get it right when I try to complete the square? It's pretty close, isn't it, to being... Yeah, it's pretty close to being nice. You know what, I'm actually going to use the square fact. I think I stand a better chance of completing the square if it's this. And that's got the same square. Because x squared is the same thing as minus x then squared. So yeah, and I think that's my preferable way around to have the minus signs. Just personal preference, right? Yeah, like this. Because then we want minus 6. Good, okay. When I hear the word maximum, I think differentiation. But we can see there's multiple things that you might think. There we go, I've gone just off the bottom of the screen. Yeah, the maximum value of cos is 1, but the cos squared throws in a bit of a spanner. But don't worry, if you complete the square, then that goes back to being a cos, doesn't it? So this is kind of telling a story about how you start with cos x and then do lots more calculations. Double it, subtract 1, square that, take off 6, square that again. Oh my goodness, what sort of values might you get? Not at all clear. The squaring has a kind of folding effect where it's not just the case that large value in, you get large value out, because I guess some of this could be negative. You know, you square a negative number, you get maybe an even larger positive number. So hello to Maya and goodbye to your 10 kid. One of them's joining, one of them's leaving. Okay, so suggestions of what to do next, I suppose. I think I want to start putting ranges on these things to think about how large things are. I've kind of got nested functions going on. What do I actually want? I want the largest value. Now, maybe the thing I've got is slightly different to yours because I did that trick of kind of bringing in an extra minus sign inside. So maybe yours is 6 minus this thing squared, but still. Oh, you take out the coefficient? Yeah. Often you've got to divide if you do that. So would you put a 4 over here somewhere? Or would you put 4 outside? Oh, I guess, yeah, maybe 4 around here. In which case you get something like cos x minus 1/2 or something. Anyway. Right, okay. So I think I want to work step by step to say, are we making this? Yeah, so maybe we want to make this as small as possible. Or maybe as large as possible. What do I want? I think I want some bounds on this. So 2 times cos x minus 1 is between minus 3 and 1, because even if cos x is as large as 1, when you square it, sorry, when you multiply by 2 and subtract 1, you get 1. So then when I square that, well, I'll get something that's between 0 and 9. Do you remember we talked about this ages ago on the episode about inequalities and algebra? That you have to be really careful with things like this. You might think that it's between 9 and 1, but actually it could go down to 0. So you just got to be careful that this square really could be, this square including the square up here really could be 0. It's not obvious from that interval, right? Minus 3 to 1, when you square it, you get everything up to 9, and you get from the middle everything down to 0, and then you get everything up to 1, kind of again on the other side. Okay, so when I subtract 6, this thing is between minus 6 and 3, and then I square it, and after squaring it, overall, this thing is between 0 and 36. I think my answer is B. I think it can be as large as 36, which happens when cos x is 1/2. Because when cos x is 1/2, that bracket 0, you get squared. And this thing, for me, it becomes very, very negative. if your expression says 6 minus something, your expression becomes very positive, and then you're squaring a very positive thing. Yeah, I want a 0 at some point. The coefficient of x term when completing the square must be 1. Can you explain why not? Okay, maybe this is not completing the square then. But the question is, why are these two things equal? And maybe this is not exactly completing the square because my coefficient isn't where you expected it to be. But I think these expressions are the same because I've grouped them together into a square. I realised from like two or three people this is not quite what they meant when they said complete the square. They meant something slightly different. But I think we've all got the same sort of expression up to factors of 4 maybe flying around inside or outside that square. Does that seem fair? Well, I thought the coefficient of x when completing the square must be 1. It's a bit awkward now. I've underlined stuff, isn't it? So if I squared this out, I would get 4 cos squared. The cross term would be -4 because it would be double the things you see, and there'd be a +1. So that's why I've subtracted 6 to get down to -5. I think I've got a correct expression. Might not quite be the one that people have got at home, but correct expression. Anyway, I think it's B. I think it's complicated, but B. That the value that's maximum comes from cos x weirdly being quite an intermediate value of like 1/2 rather than 1 or -1. That's somewhere in the middle. If you set cos x to be 1/2, then it just turns out that that's the best thing to do overall. By tracking inequalities very carefully, twice in here I had something that could be negative or positive, and then we squared it. And after squaring, you've got to remember that the thing could be 0. Let's just illustrate that one more time because I think it's important enough that we're good. Here's a graph of x squared. And if you have some range where you know the value of x is limited to some particular range around here like this, then the value of y squared, the value of x squared, well, could be up here, could be all the way up here somewhere. So you might think that looking on the y-axis, you might think that the interval for what could y be would be up here and down here, but actually x could be somewhere over here. X could be somewhere here, or it could be all the way in the middle, and then the value would be 0. So in fact, the interval for what you can get for y goes all the way down to 0, even though that's not in between the values at the endpoints of your original interval. You had some limits on x, and then when you square everything, you can still get really small numbers from squaring those small 0 numbers, if your interval includes 0. Okay, lots of people have got B as well. So yeah, we're learning about, Sophie's got a good way of putting it. I think they tell you to make the coefficient 1 because the only other number it works with, yeah, just teach you to always have 1. So if you see, let's try and do it everybody else this way. Was there a minus sign? There was a minus sign. It's a good practice for me. So everybody else's way is something like this. I don't know whether or not you might take out this bit. Oh, I'm down here somewhere, sorry. I think everybody else's method is something like this, which is then this. I don't know if I'm making it worse by talking about it. -1/4, -5/4. And then I guess maybe you could multiply that outside bit by 4 if you wanted to. Is it complicated because people have actually got this? Probably complicated if people have got actually this. And then there's also a minus sign everywhere. What if you have y as minus x squared? Yeah, so that minus sign would, I'd apply that afterwards to flip all the values. I think of that as a 2-step process. if you have y is minus x squared. Okay, right, good. I think B in the end, and it might be fun to plot that in Desmos, maybe play around with the values or something. Okay. Next one, I'm going to switch to this view for this one, so I can show you all 5 graphs at the same time. We're looking for the graph of cos squared x equals cos squared y. That means all of the points with coordinates x and y such that cos squared of the x coordinate is equal to cos squared of the y coordinate. That maybe sounds a bit weird, but that's literally what you do whenever you sketch a graph. You're showing me all of the points x comma y such that what you've normally got is y as a function of x, and what you've normally got is all the points x comma y such that the x coordinate is x and the y coordinate is that function of x. But here we're looking at instead cos squared x equals cos squared y. So easy, because the question is this the same thing as cos x being equal to cos y? I guess almost, because squares of numbers being equal is something to be careful with. Yep, x equals y is definitely a solution. If x and y are the same number, forgetting about coordinates for a moment, if x and y are the same number, then they've got the same value of cos squared. Cos squared x would be equal to cos squared y if x equals y. That's an algebra statement, or a computation statement or something. And then separately, graph sketching question, where are the points where x is equal to y? When you think about it, x equal to y on the line y equals x, which is a straight line through the origin, which A and D do not have. Myers, no, who's this? Yeah, Myers got the line y equals minus x. That works as well, because if y is negative x, then on the one hand we've got cos squared x, and on the other side of the equation we would have cos squared of minus x. But cos of minus x is just the same thing as cos of x, so those would agree. So then graph sketching question, where are the points where y is negative x? And we've got a line of negative gradient that goes through the origin. Most of the graphs have got that one as well. Other facts about cos will help. For example, it's periodic. Anna in chat tells me that one of these pictures is not periodic. In fact, like, I think 3 of them are not very periodic in the right way. But if x comma y is a little solution, if those values work, then brilliant. You've maybe worked really hard to find a value of x and a value of y, where cos squared x is equal to cos squared y. And then if you add, let's think about it, but if you add a particular number of degrees, then cos squared x will change. If you add, you do a transformation to move parallel to the x-axis, you add some value to x, you might get back to the same value of cos squared x. So when does that happen? This graph should be periodic, that if you translate by just the right amount to the left or the right, then you're taking something which is cos squared x, and you're going to get back the same values, so it will also be a solution. So how far should we translate it then? So this is the question, I guess. I mean, we could go and solve the thing. We could go and work out exactly where all the solutions are, but if you just want to think about translations, then D and E are out. They don't have translational symmetry at all. I think it's just between B and C. How far should I translate it? And there's a couple of people telling me that it's 180 degrees. Cosine x has normally got period 360 degrees. So if you were thinking that at home, then you're onto something, because shifting by 360 degrees would give me another solution. That's the period of cosine. But because the thing in the question is cos squared, values repeat more frequently than that. Squaring sends negative values to positive values, which means, I suppose, that shifting by 180 degrees, cos of x plus 180 is the same thing as cos of x. No, it's negative. Whoops. Rewind. Cos of x plus 180 is negative cos of x. But if we're going to square cos x squared on the left there, if we're going to square, then who cares about minus sign? So that will come back again. Maybe I think we should solve this. I'm not sure, but maybe we should. I think something we could do to try and solve this is we could try and work with the algebra, right? So I think the answer is C, that we want quite a lot of lines. But let's work out why. So we have cos squared x is equal to cos squared y. So if I rearrange this, then this is the difference of two squares. So I get cos x minus cos y, cos x plus cos y is equal to 0, which works out to say that cos x is plus or minus cos y. Oh, look, I should have just thought about the square roots up here, thought about square roots carefully. That if their squares are equal, then their values are equal up to minus signs, plus or minus sign. So first let's think about cos x equals cos y, or cos y is cos x. That means that x and y are two numbers. I don't really want to label my axes on this picture, but x and y are two numbers which might be the same, or it might be the case that y is 360 degrees more than x, which is that translation we've been talking about, or it might be the case over here, kind of more interesting, that y is just as much less than 360 degrees as x was more than 0, which is a stupid way of me saying that it's 360 minus x. So this gives you some different lines. The y might be x plus 360, y might be 360 degrees minus x, and then there's a bunch more possibilities. These things repeat, which gives us lots of sort of straight lines, either increasing or decreasing. It gives us, I think, all the stuff in picture B. And then there's the other case where cos y is minus cos x, where you need to think about whether this value is equal to this value down here, and up to minus signs. That gives you the other lines in the picture. That's where they come from. Yeah, bonus question is to work out what on earth E is supposed to be. So A is clearly a bunch of sine and cosine waves on top of each other. B and C are different amounts of straight lines. D is the same as A, but the other way around. And then E is quite a lot of circles and hyperbola. It's a lot of different curves that either have x squared plus y squared is constant, or that have x squared minus y squared constant, or that have x squared equals y squared, which I guess is the second case, all on top of each other with different constants, possibly counting numbers. Anyway, what a weird picture. Fun fact, I recreated that picture from the I had a picture of the old math question, but I recreated it to have it nicely formatted in black and white on the MAT Livestream. So I had to work out what option E was. Oh yeah, sorry, what's a hyperbola? Not on that. Somehow weirdly there's a picture of one on a MAT question. You don't need to know this, but a hyperbola is a graph y squared minus x squared equals constant. So something like, you've seen circles, now get ready for y squared minus x squared, or you could say x squared minus y squared with a difference in. They tend to look like this. Hyperbola. They're pretty cool. You don't need to know the word hyperbola, you don't need to know how to sketch one, but I'd like to have some fun with that. Good, okay. Oh, is it cos of y squared equals cos of x squared? That would be good. Ooh, oh, they got the wrong number of cos squares in. That'd be good. Yeah, possibly it's that. There's a suggestion in chat of what might be going on, which, if I think about it, might have saved me some time. Right, okay, we're going to spend about a minute on this question. because we're going to try and knock this question out straight away by saying when you see cos nx, I think the notation is not amazing for this sort of thing, is it? That means cos the n. And when you see cos 2nx, fun fact, Desmos doesn't actually accept these. Desmos forces you to type it the kind of tidy way like this, which is then obviously like cos x to the n squared. So probably I've got bored of writing cos x to the n, and I would like to write something like this. So just give it a new name. Let u be this thing here, and then it's a quadratic. Good. One vote for hidden quadratic in chat. Yep, some sort of quadratic. Looking for solutions. And then the solution is just u equals 0 or u equals -1. Don't miss 0 when you do this. The 0 solution is not very interesting. It just means that cos x is 0, which you can go and solve. You're fine at solving that sort of thing. This one is interesting. This says cos x to the n is -1, which is like not possible if n is even. But then if n is odd, you pick up some extra solutions. If n is even, then this just doesn't work, right? Because if n is even, then you've got a square on the left, and squares are positive or 0. So it's not possible if n is even. But you get some more solutions. I think the only option where you get more solutions if n is odd is option D. We should probably go and calculate them, but maybe I'll leave that as an exercise. I mean, you know when cos x is 0, you know when cos x is -1. It's going to be okay. It's another appearance of one of my favourite things, which is -1 to the power of n. -1 to the power of n is a great sequence. Don't try to add all of its terms together, but it's just really nice. It goes 1, -1, 1, -1. Sometimes that's just what you wanted. Yeah, we can calculate much further. We can do much better than this. I've got lazy at the end here. I'm sort of suggesting that instead of drawing a little smiley face, that you calculate. Sorry, anonymous person says it's possible to calculate further, and yeah, absolutely. Go to it. Get on that. Please calculate for me, exactly the values of x where this thing works in the range 0 to 360 degrees. Okay, we should pay attention, I suppose, to what the range is. 0 to 360, right. Okay, but that's the short questions that we've got for today. We've got half an hour, and we've got some long questions to look at. Let's put them on the screen. There is some calculation about a triangle. Let's put it full screen. There we go. Oh, there we go. Full screen question about a triangle with these areas. We did some stuff on areas involving circles last week. There's this slightly common thing that you find yourself doing where you have a region with some curved boundary made of a circle, and you split it into bits that are circle and bits that are triangle to sort of split things up. I suppose that the kind of key diagram is that if you have two radii marked on your circle, maybe to 2 points of interest from the origin, if you have two radii, then you could think of those as being two sides of a triangle. Find the area of that triangle because you're good at that. Or you could think of those as two sides of a sector of a circle and find the area of that because you're good at that calculation as well. And if you can do both of those, then you can combine those kind of pieces together to find the area that's in one but not the other, which is a kind of weird sliver of space around the edge of the circle. You can do this sort of question as well. Thank you in chat 90 to 70 for even numbers, and you get bonus solutions. Where are the bonus solutions? And -1? You mean cos x is -1, right? I'm very confused by that chat comment actually. No, I'm good. You're right. 90 to 70, and you don't mean -1. You mean 180. You mean u is -1. Right, good. Okay. So we can talk about this question if you like. It's got these areas A theta and B theta, or we could kind of skip down to the ideas. There's some parts of this that I just sort of trust that you can do. So maybe I'll skim down and let you look at what we're being asked to do. over here, and maybe you could let me know in the live chat audience whether you want to do bits of this question. There are some things that are similar to the calculations we've done before, and different things. Kuga asks if you can write in radians, and yes, you are allowed to use radians. I'm not allowed to use radians when I write the questions. You are allowed to use radians when you do the questions. The funny thing is that maybe both you and I know about radians, but it doesn't ever, I think, really help to use radians. I mean, they're kind of, I'm joking a lot about radians, but they are nice, but they're kind of just the same. It's a bit like asking whether you can do your rough working in French. Like, you're not going to hand in your rough working, so yes, you can do it in French. If that makes things easier for you to have your working out in French, then fine. The rough work on the page, do that in French if you like. Now I feel like I have to say that for the typing the answers bit, you must type your answers in English, making this point about doing the rough work however you like for your rough work. Okay. Request for part 2. Question about CS applicants. So everybody this year is doing the same questions on the MAT. In 2024, there is a collection of questions and everyone will do the same questions. The people writing the questions are aware of that. The people selecting questions are aware of that. My test is being designed to be appropriate for all maths and computer science applicants at the University of Oxford. Right, request for part 2, which I need to read off my page because that is grainy for me. Explain why these areas have some relationship between them and find for me A of 45 degrees. Okay, let's talk about that. So I'm going to put this here, but I'm going to probably scroll back up again to have a look at what A of theta is. I'm going to put that there so I can do some whiteboard stuff. I guess I could redraw a picture. So a small one over here. Okay. Oh, this is terrible. I should have drawn the circle first. Bad circle. Right. Okay. A of theta, B of theta. So the question is to talk about B of 90 minus theta, and it looks maybe a bit like we're supposed to calculate both of those things and then check that when you put in 90 minus theta into your B thing, you might find A of theta. But you can do better than that. You can do something slightly easier, I think. So these are defined in terms of theta, which is this angle down here. But there is a 90 minus theta in the picture. The 90 minus theta is up here. There it is. Okay, so it's got nothing to do with A and B at the moment. I've just marked in an angle that's 90 degrees minus theta. Progress, right? The question says 90 minus theta. Now we have a 90 minus theta. We've got to do something with it. And I think the right thing to do is to look at the triangle from that point of view. So what we've got here is a right angle triangle with a circle in it, and there's some area nearby this angle and some area on the other side. And that makes me think that if I redrew the triangle the other way around, I'd have over here 90 minus theta. I'd have up here theta, I guess. It's gone slightly off the screen. There you go. What a tall triangle. And you'd have a circle over here. And I suppose there's two ways that I could label this. I could say, well, this is exactly the situation in the question. So this thing is, in the question, this is called A of the angle. And this is called B of the angle. And okay, now the angle has got a funny name. It's now called 90 minus theta. Labeling it like this because of, well, the question says that this area near your lower angle is called A of that thing. So it's called B of that thing. But on the other hand, this is the same triangle. Corporate wants you to find the difference between these two pictures. It's the same picture. This is theta, so this really is still after looking at it the other way around, just a of theta. And this is still b of theta. It's just the triangle has been turned over, flipped into a different position. So it must be the case that a of theta, a of theta is the same thing as b of 90 minus theta, because they're both describing the same area. So in an explaining question where I have to type my answer, I would type some of that. I would say something like, looking at the triangle from the other angle, we are in a situation where we have the angle 90 minus theta. I guess I can't type theta, the question would be written without the letter theta, but whatever, 90 minus t. And the angle near this, the area near this angle is b of 90 minus t. On the other hand, clearly a of t, because that's what it is in the question. Right, okay, we're also asked for a of 45. So I think my first guess is that I should set theta to be equal to 45 degrees. And that does seem like quite a good guess, because in that case, a of 45 degrees would be b of 45 degrees. So those two areas are the same, which I guess I know, because in that case it's an isosceles triangle. This isosceles triangle case, I don't think there's any surprise that these two areas are the same. And better than that, right? I know I can mark in some radiuses. Should probably have done that before, to mark in some radiuses, and then I can start to build this picture where I've got, I don't know, maybe I'll put that one in as well. I've got some angles that I can find, because this is a 45-degree triangle. I've got some angles I can find. I've got this little square down here. That's nice if I'm talking about areas, because squares, I know how large they are, except for the square of 14, which will always evade me. 45 degrees over here, and we're trying to find these areas on these two sides. For people not here last week, I had real trouble squaring the number 14, which has happened to me a couple of times in my life on camera, that I have failed to square the number 14. So people in chat threatened to make it a running joke, so I'm trying to lean into it. Right, okay. Different bits of area. I don't think this is going to be too bad. I think I'm going to take something like the area of the whole triangle, maybe minus the square, minus 3/4 of a circle, and then divide by 2, because they're equal. I would like to use that fact. I feel like dividing by 2 at the end is a clever thing to do. So I'm trying to subtract off this square and this kind of Pac-Man shape in here. So if you look at it from the side, it's Pac-Man eating a square, and I would like to subtract both of those things and then divide by 2. Shouldn't be too bad. Sorry, we're just changing which one we label as A and B in relation to which angle we look at. Yeah, I've got two pictures, and if you like, these are two totally different triangles with theta and different letter. Maybe I could disguise it. Maybe I could say phi, like nothing to see here. I've got two pictures, theta and phi. They're showing me the A of theta in the theta case and A of phi in the second case. And of course that would be B of phi in the second case. Yeah, nothing to see here, nothing to see here. And then, whoa, reveal, phi, what if it's equal to 90 minus theta all along? Then the two pictures are actually the same triangle. So I get this extra way to label it, to say, if that second angle, phi, that I told you about was 90 minus theta, then it would be exactly the same triangle the other way around. In which case, surprise, A and B of theta, you could label them as being exactly the same area that's just been flipped. I'm doing that. This is my way of illustrating a reflection in the line y equals x, which is precisely what's happened, if you want. Will the typing questions be topic specific before or random, like question 5s? Believe it or not, that is not an official part of the MAT. There's no rule that says that question 5 was random. I'm amused by the idea that question 5 in general was random. I think all 27 questions on the MAT have access to the same mathematics from the MAT syllabus. Whether or not any particular question uses lots of the things from the syllabus or not so much is the question. Fun fact, we don't actually have aircon. We have an enormous tank of water somewhere, which stabilizes the temperature. It's great. Just inertia. Right, there was a question about finding the line OPQ, which I think is a bit more interesting than I could do this A of 60 degrees calculation. I just know it's going to be something like you have a triangle, circle, there's 60 degrees, you know lots of angles, that's 120 degrees, you know chunks of circle, you could do some subtraction, you've got some right angled triangles hanging around here, and you don't want to see me do that calculation. So maybe I want to think about that first part quickly. The equation of the line PQR. So P and Q and R are all on a straight line. Let's go back to this view just a second. P and Q and R are all on a straight line, and you want the equation. So you know the gradient is minus tan theta, and you know that it goes through the point Q. That should be enough, right? Because once you know the gradient and a point that it goes through, you should be able to write down that equation. As for the coordinates of Q, I would draw a line from the origin of the circle, because you know exactly where that is. So it's got radius 1? Yes, it does. Up here somewhere, radius 1, and it's at 1, 1. So you know exactly where the centre is. That's solid, fixed, kind of reliable circle. I'd draw a radius out to Q, and then I would think about angles and try and chase how's that kind of tilt to where Q is related to theta. It's got to be something to do with theta. So try and chase some angles around to find out how that's related to theta, and then hopefully it's just sort of trigonometry for where the, relative to 1, 1, apparently it is add on a bit of sine theta, add on a bit of cos theta, which suggests that it's at 1, 1 plus a little bit. If you like vectors, then that's a vector to 1, 1 plus a vector from 1, 1 to Q. Do you have to get the equation of the line the way it's written in the solutions? No. Do the solutions do something weird? There are many ways to write the equation of a line. All of them were acceptable the year this was used as a math question, I am sure. And the solutions on the MAT Livestream page have written this in a mad format. Y is minus tan of brackets x minus 1 minus sine theta close brackets plus 1 plus cos theta, and not simplified. Yeah, sorry, the solutions on the MAT Live website haven't bothered simplifying at all. So you might have simplified. Okay. Sorry, anonymous person, for any confusion caused. Right, okay. I think we're good. Areas. I've kind of skipped the bit of this question. It's a little sad. I've skipped the bit of this question where we chase angles around and we find areas of bits of circle, and that's because we did lots of areas of bits of circle last week, and also I think you're really good at it. If I show you 120 degrees at the centre of a circle, there's very little mystery about how much of the circle is inside that bit of the circle. Right, so let's have a quick look at, look at all these hints, if you would like the hints for this sheet or for previous sheets, or for next week's sheet. You can see those on the MAT Live website. And a tiny extension. Oh yeah, the extension is to actually calculate it, because I think it's not that hard. I think you can actually do it. That's not part of the math question. I reckon you can do that in general. That's me. There's me. That's just confidence in your abilities to write down how large part of a circle is. General case is just not that much. Okay. There's some trigonometry in here, but I think we need to skip through to get to the trigonometry. So this is perfectly fine. If you want to use this as practice for coordinate geometry, for differentiation, some tangent stuff going on, it's perfectly fine for that. There's a gradient of a line, which is given by rise over the run. There's coordinates of B. How does that work? Oh yeah, we're joining something to the centre of the circle, and then it's at this kind of point where once we've worked out where B is, there's then a bunch of stuff about these areas. Yeah, so I thought maybe we could talk about this, and then there's some sort of algebra stuff at the end. Anna's seen that and calling it a day. I think I've got 10 minutes on the clock, so I should talk about some of this. Maybe part 3. Let's talk about part 3. because I think that's the hard bit. So the situation so far, when you get down to part 3, I'm trying to skip the first 2 bits. I think they're not very exciting. If you skip down to there, then the situation is that we have a circle. We know where the circle is. It's got centre at 0, 2. We know its radius. So no, we don't know its radius yet, but we do know a point on the circle. It's called B, and that point is at, we have worked out in part 2, square root of 3/2, comma 3/2. The pattern there and its coordinates is because it's on the parabola, that equals x squared. And we are asked a question about the triangle, or sorry, the area of the sector that goes from that point to A on the other side. Okay, I've been muttering while I draw a picture. There you go. So we kind of know where everything is. A is on the other side. The picture's symmetric. So A is at minus square root 3/2, comma 3/2. So we know where everything is. We just want, well, really we want this angle, don't we? And I suppose that's the trigonometry part of this, to work out what theta is. So suggestions in chat. I found this previous long question from 2012, put it on the trigonometry sheet, really just because of this bit, this kind of moment. If you know theta, then this turns into a sort of angle of some sort of, what is this? What am I saying? That's an area of a sector, part of a circle, if you know the angle theta. And there's at least 2 ways to do this. I'll take a question quickly, because somebody says, does Oxford consider maths, computer science and further maths as 3 separate A-levels? Maths, computer science and further maths as 3 separate A-levels? Yes, those are 3 separate A-levels. If anybody tells you otherwise, take your A-levels, get the qualification, get the certificates for your 3 separate A-levels and show them. 3 separate A-levels. No, we really do. I can't stress this enough that we count maths and further maths as 2 A-levels because they're 2 A-levels. They've got similar names, but we count them as 2 A-levels. So Oxford is fine with, if you're applying for maths, then we're telling you to do maths. We're really strongly encouraging people to do further maths. Highly recommended. And we know that that's already quite a lot to ask for. Some people only get to do 3 A-levels. Depends which school you're at. Some people only get to do 3 A-levels, so that's almost all your choices taken up by, in my opinion, an excellent choice to do lots of maths. But for some people that's a lot of choices taken up. Yeah, so then Sophie suggests that maybe employers might think of maths and further maths as only 1 A-level, but I don't really know. Well, I suppose I don't know, do I? I don't know anything about how employers feel about A-levels. Part of me thinks that if you're doing further maths, then you're probably quite good at maths. Might also enjoy other stuff, but you know, not everybody gets to do 3. Not everybody gets to do a 4th. Yeah, okay. So suggestions in chat. Find the length of the radii and the length AB. That'd be excellent. Should I give that a name? I'm going to call that O. That might help you in chat explain which triangles you wanted. If you find the length of AB, and also, I guess, AO, and also OB, then you might be able to find the theta using the cosine rule. If your school doesn't do further maths, to answer a question in chat, if your school doesn't do further maths, then the standard Oxford offer is for maths at Oxford, A star in maths, A in any 2 other subjects, and you're encouraged to please let us know either in your personal statement or in your UCAS teacher's reference that your school doesn't teach further maths. You didn't have the opportunity to do further maths. There's quite a lot of stuff. If you want to just see some of it online, I'm saying this because you've come here to see this sort of maths online. There are other resources online where you can see a little bit of further maths if you want to. But we know that it might be the case that somebody is a really strong student who happens to be at a school where you can't do further maths, been missing out on complex numbers and stuff. I wrote cosine rule on the screen just off the bottom. There you go. Yeah, there are two expressions here because you have this alternative where you might choose to drop a perpendicular like this. You might say, I don't know anything about A, but I do know that this point over here, I can work out where this point is, find this height, and then talk about find this angle, and then kind of there's a factor of 2 from sort of doubling up which sector of the circle we're talking about. So if I put it in the circle, some people might find this angle and only work on this sector, which is why there's some factors of 2. Good. Hey, right. Yeah, so School Doesn't Do Further Maths offers based on maths. Please do maths A-level. Is it compulsory to get A star in further maths? The standard offer for maths at Oxford wants A star in further maths. If you're doing further maths, then it's the standard offer is to ask students to get A star in that. If you aren't doing further maths, then we can't ask for a grade in it. But if you're doing further maths, if it's taught at your school and you're going to the lessons and you're revising for the exam, then it's possible that if you get an offer to study maths at Oxford, that you'll be asked to try to get A star in further maths. That's their kind of standard thing that we ask people to do when we make them offers. We've currently got people who we made offers to in January. We asked, I think, essentially all of them to get A star in further maths out of the people doing A levels, and we're going to find out in a few weeks for results day. We're going to find out if that happened, and my prediction is that it will have happened. That'll be good. Right, if you get A in maths but A star in further maths, that is technically possible. That would be a surprise, and probably technically that wouldn't meet the standard conditional offer, which the standard conditional offer wants you to get A star in maths and A star in further maths, like and both. It's unusual. It has happened. In all of these cases, if somebody misses their offer in a month's time, I'm really sorry. If you're in year 13 watching this, and it's very traumatic of me to mention this, but if somebody misses their A-levels, then the college might be able to take them anyway, but they don't have to, especially if they don't want to, I suppose. What's an ideal MAT score? So the MAT is marked out of 100. Ideal, I'm interpreting as perfect, which is 100. That would be ideal. Aim for the top. Then if you miss, then yeah. Higher MAT scores are better. I usually say that about 70 is a good score, but there's no point at which tutors think that you've scored too high. The tutors are in general would always like to see more scoring. We seem to be doing question and answer now, which is fine. I reckon people know the cosine rule or enough to apply it to one of these triangles to get to one of the two expressions on the board. So we'll let's turn chat back on. Let's have a look at questions. There, you see the questions that I've been talking to. You can. Sorry for the YouTube audience, I've been having a chat with people just off screen over this direction. TMUA. Oxford does not need you to take TMUA. I don't know anything about it. Sorry. Sorry, I took questions and now it's immediately one where I don't know anything about it. So, nothing to do with me. Sophie has completed my quote. Thank you, Sophie. Reach for the stars. Yeah, this is it. Even if you miss, you'll land on the moon. Is that a thing? That sounds like a thing. Could be a MAT score thing. Is Is it the other way around in the phrase? Is it shoot for the moon, and even if you miss, you'll be among the stars? I think it might be that way around. Okay. For computer science at Oxford, yes, so I've been saying A star in math, A star in further maths quite a lot. I've been saying A star in maths, A star in further maths quite a lot, which is the standard conditional offer for maths. For computer science, it's a little bit different. They are looking for 1 A star, which should be in maths or further maths if you're taking those courses. They have a slightly different policy on further maths. I suppose I should clarify that I'm calling in from the maths department, where we are extremely keen on further maths. The computer science department are also very keen on further maths, but their standard offers are slightly different. So there you go. Yeah, there you go. Okay. Good book for interesting and out of the box problems. No, but I will think about it. Interesting and out of the box problems. Makes me want to suggest an interesting and out of the box book with problems. When I was a teenager, I had a couple of books. No, did I have them? Did I borrow them? Where did I get these books from? Might have been borrowed from school, actually, from school library or something. Anyway, the UKMT in the UK, the UKMT makes these books of lots and lots of problems, and I think some of them are a bit kind of hard to tell what's going on. They're difficult. The problems are on different topics, but then I think some of the books are on other stuff as well. Ian Stewart is a good shout as well. Thank you. Yeah. Good, right. And Moses has brought us back to trigonometry to wrap this up. Thank you, Moses. Shoot for the stars, and if you miss, then adjust your angles and try again. We've learnt today that you can look at triangles from two different angles. That might be a good way to get a new angle on a problem. We've seen the cosine rule, we've seen the sine rule. We've briefly thought about whether or not we could invent a tan rule. We've graphed some functions. Have some fun with inequalities, and we're going to do it all again. We're going to do it all again next week in 167 hours. 166 hours. 166 hours for sequences and series on the MAT Livestream. So we will see you then. If you want to see the worksheet in advance, it's on the website now. Practice test is on the MAT website. Scratch the LIVE, it's not part of the live stream if you want to see a practice test, but as I said, don't get too excited. It is just past questions in a pretty straightforward online format. Right, thank you everyone, take care, have a good weekend, see you next week, bye.